Most people believe the solar system ends at the last planet. Neptune marks the boundary, and beyond it, there is nothing but empty space stretching towards the nearest star. That idea is completely wrong. In 1977, NASA launched 2 small spacecraft on a journey that was never supposed to go this far. But Voyager kept flying. Past Jupiter, past Saturn, past Neptune, and then, decades later, into a region no instrument had ever touched. What those spacecraft found was not silence. It was a boundary. An invisible wall of particles, plasma, and magnetic force, where the sun's influence finally gives way to something older and colder. The edge of the solar system is real, and what Voyager measured there changes everything we thought we knew about where we live. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, are you comfortable? Let's begin. If someone asked you to draw the edge of the solar system, you would probably draw a circle around the last planet, Neptune. Maybe if you were raised before 2006, you would have drawn it around Pluto. Either way, there would be a line, and beyond that line, the solar system would end, and empty space would begin. That is the picture most of us carry in our heads. A neat arrangement of planets orbiting the sun, bounded by the outermost orbit, surrounded by the void. It feels clean. It feels intuitive, and it is fundamentally completely wrong. The solar system does not end at Neptune. It does not end at Pluto. It does not end at any object you could point a telescope at and photograph. The real boundary of the solar system is invisible. It is made not of rock or ice or gas, but of particles, magnetic fields, and plasma. It exists billions of miles beyond the last planet, in a region so remote that even light from the sun takes more than 16 hours to reach it. And for most of human history, we did not even know this boundary was there. We had theories, we had mathematical predictions, we had suspicions rooted in physics, but we had no direct evidence. No instrument had ever touched the place where the sun's influence actually fades. That changed because of 2 spacecraft that were never designed to go there. And what they found when they arrived rewrote our understanding of where we live. To understand what Voyager discovered at the edge, you first need to understand something about the sun that most people never consider. When you look up at the sun, you see a ball of light. A hot, bright sphere sitting at the center of the solar system, providing warmth and energy to everything that orbits around it. That picture is true, but it is drastically incomplete. The sun is not just a source of light. It is a continuously erupting engine of plasma and magnetism, and its influence extends far beyond anything your eyes can detect. It reaches out across the entire solar system, past every planet, past the Kuiper Belt, past the frozen debris at the outer edges of known space, and keeps going. The sun is not just shining on its planets, it is actively filling the space around them with its own material. Every second of every day, the sun ejects roughly 1 million tons of charged particles from its outer atmosphere. These particles, mostly protons and electrons, stream outward in all directions at speeds between 300 and 800 kilometers per second, depending on the conditions at the solar surface and the phase of the sun's activity cycle. This relentless outflow is called the solar wind, and it never stops. It has been blowing continuously for approximately 4.5 billion years. since the sun first ignited its fusion core and began converting hydrogen into helium. The solar wind is not gentle. At Earth's distance, it is a supersonic torrent of ionized gas, thinned by distance but still carrying substantial energy and momentum as it rushes past. And the solar wind carries something else with it, something that matters enormously to this story. The sun has a magnetic field, generated deep in its interior by the churning convective motion of electrically conducting plasma. That magnetic field does not stay confined to the sun's surface. It is embedded in the solar wind, frozen into the outflowing plasma by a principle of magnetohydrodynamics, and dragged outward as the particles stream away from the sun in every direction. Because the sun rotates, completing one full turn approximately every 27 days, the outward streaming magnetic field lines get wound into a vast spiral pattern, stretching from the sun's surface outward through the entire solar system and beyond. This spiral structure is called the Parker spiral, named after the physicist Eugene Parker, who predicted it in 1958, years before any spacecraft confirmed its existence. The result is that the sun does not merely illuminate the solar system, it fills it. Solar wind and the magnetic field it carries permeate the space between the planets, creating an environment that is continuously shaped and controlled by the sun's output. When the sun erupts in a major flare or hurls a massive blob of plasma called a coronal mass ejection, the solar wind intensifies and the magnetic field distorts. When the sun quiets down during the low points of its roughly 11-year activity cycle, the solar wind weakens and the magnetic field relaxes. The entire region around the sun, out to distances that make the planetary orbits look small, is a domain of solar influence. A volume of space defined not by the orbiting bodies inside it, but by the reach of the sun's particle and magnetic output. This domain has a name. It is called the heliosphere. The heliosphere is a bubble, not a glass bubble or a membrane you could touch, but a bubble in the plasma physics sense. It is a region of space inflated by the continuous outward pressure of the solar wind, embedded within a larger medium that pushes back against it from the outside. That larger medium is called the interstellar medium. It is the thin gas, dust, and magnetic field that occupies the vast spaces between the stars of our galaxy. When you look up at the night sky and see the darkness between stars, that darkness is not truly empty. The interstellar medium fills it. It is extraordinarily sparse by human standards, just a fraction of an atom per cubic centimeter in some regions, a handful per cubic centimeter in others, but it is there. It is made mostly of hydrogen and helium, with trace amount of heavier elements forged in the cores of ancient stars that exploded long before our solar system formed. It also carries its own magnetic field, separate from and unrelated to the sun's field, threaded through the galaxy by processes that stretch across thousands of light years. And it has pressure. The interstellar medium pushes inward against the sun's outward flow, resisting the expansion of the heliosphere at every point along its outer surface. The sun is continuously blowing outward. The interstellar medium is continuously pressing inward. At some enormous distance from the sun, those two pressures reach a balance. The outward push of the solar wind equals the inward push of the interstellar environment. That balance point defines the outer boundary of the heliosphere. Everything inside that boundary is solar territory, a region dominated by the sun's particles and fields. Everything outside it belongs to the galaxy, controlled by the interstellar medium and the magnetic fields that thread through interstellar space. The Sun carved this bubble out of the surrounding galactic material billions of years ago, when it first began generating its solar wind, and it has maintained it ever since by continuously pumping particles and energy outward. The heliosphere is not static. It is dynamic, breathing in and out with the Sun's 11-year activity cycle. When the Sun is at solar maximum, erupting with flares and coronal mass ejections, the solar wind strengthens and the heliosphere inflates slightly, pushing the boundary outward. When the Sun is at solar minimum, quieter and calmer, the solar wind weakens and the boundary contracts inward. The heliosphere is also moving. The Sun is not stationary in the galaxy. It is traveling through the local interstellar medium at approximately 26 kilometers per second, plowing through the surrounding gas like a boat through water. This motion compresses the heliosphere on the leading side, the direction the Sun is heading, and stretches it out on the trailing side. The bubble is not perfectly round. It is shaped by the interaction between the Sun's output, its motion, and the properties of the interstellar medium it is moving through. If the Sun stopped blowing its solar wind tomorrow, the heliosphere would collapse inward, squeezed shut by the interstellar medium, probably within a few years. Without the solar wind, there would be no bubble at all. This boundary is real. It is physical. It exists at a specific, measurable location in space, and in principle, a spacecraft could fly through it. But you could never see it. There is nothing to photograph. No wall, no glowing edge, no line painted across the darkness. The boundary reveals itself only through changes in what surrounds you. On one side, the particles are solar particles, relatively hot and fast, blown outward from the Sun. On the other side, the particles are interstellar particles, cooler and denser, part of a galactic background that has existed since long before our solar system formed. On one side, the magnetic field belongs to the Sun, wound into its characteristic spiral. On the other side, the magnetic field belongs to the interstellar medium, oriented in a direction that has nothing to do with our star. To detect this boundary, you would need instruments capable of measuring the density, speed, temperature, and composition of the particles around you, along with the strength and direction of the magnetic field. You would need to track how those measurements change over time as you move outward. And you would need to be unimaginably far from the Sun, far beyond the orbits of every known planet, out in a region so remote that the Sun itself is just a bright star in the sky behind you. No telescope on Earth or in orbit around it can make these measurements. The boundary is too far away and too diffuse to observe remotely. You cannot see the wall of your room by standing in its center and squinting. You have to walk to the wall and put your hand against it. The only way to find the edge of the heliosphere is to send something there and let it feel its way through. But the boundary is not a simple wall with a clean inside and a clean outside. It has structure, layers, a graduated transition zone that spans billions of miles. Understanding that structure is essential to understanding what Voyager eventually measured. The first layer is called the termination shock. As the solar wind rushes outward from the Sun, it is supersonic. The particles are traveling faster than the speed of pressure waves in the surrounding plasma, much like a bullet moving faster than the speed of sound through air. The solar wind has been supersonic since it left the Sun's corona, and it stays that way for billions of miles. But as it pushes deeper into the mounting resistance of the interstellar medium, the solar wind cannot maintain that speed forever. At roughly 80 to 100 astronomical units from the Sun, the solar wind slams into a kind of invisible threshold where the accumulated back pressure becomes too great. The flow decelerates abruptly from supersonic to subsonic speeds, releasing energy in the process. The plasma heats up dramatically. The magnetic field compresses and strengthens. Particles that were streaming freely are suddenly caught in a congested, turbulent flow. The character of the solar wind transforms from a fast, clean outward stream to something slower, hotter, and far more chaotic. This abrupt deceleration is the termination shock. Crossing it does not mean you have left the heliosphere. It means you have entered its outermost region, the beginning of the end of the sun's reach, where the solar wind is no longer free-flowing, but is piling up against the resistance ahead, like traffic compressing behind an invisible barrier on an open highway. Beyond the termination shock lies the heliosheath. This is the thick, turbulent layer between the shock and the outer boundary. In the heliosheath, the solar wind is still present, but it has been profoundly altered. It has been slowed, heated, compressed, and redirected by the mounting pressure of the interstellar medium pressing inward. The plasma in the heliosheath does not flow radially outward in clean lines anymore. It gets deflected sideways and eventually turns to flow along the boundary, like a river hitting a cliff and spreading out along its base. The heliosheath is chaotic, with fluctuating temperatures, densities, and magnetic field directions that vary from month to month. It is a transitional environment, dominated by forces that are neither fully solar nor fully interstellar, but a messy collision between the two. And beyond the heliosheath, at the very outermost layer, is the heliopause. This is the true outer membrane of the heliosphere, the boundary where the outward pressure of the solar wind is finally equaled and stopped by the inward pressure of the interstellar medium. The density of charged particles jumps sharply at the heliopause because the interstellar medium, while incredibly sparse by everyday standards, is far denser than the exhausted, stretched thin solar wind at that distance. It is here that the sun's material finally gives way to the galaxies. The magnetic field may change direction, the temperature changes, the entire environment shifts from solar to galactic. This three-layered structure, termination shock, heliosheath, and heliopause, was predicted by theoretical physicists beginning in the 1950s. In 1955, physicist Leverett Davis proposed that the sun's magnetic influence must create a cavity in the surrounding interstellar gas. In 1958, Eugene Parker predicted the existence of the solar wind itself and developed the mathematical framework for how it expands outward and must eventually be stopped by external pressure. By the 1980s and 90s, increasingly sophisticated computer simulations were producing detailed maps of the heliosphere's expected structure, showing where the termination shock should form, how thick the heliosheath might be, and where the heliopause should lie. The physics was well grounded. The predictions were specific and quantitative. But for the entire second half of the 20th century, every single detail of this structure existed only in equations and simulations. No spacecraft had ever been far enough from the sun to encounter any of these boundaries. No instrument had ever directly sampled the termination shock, measured the turbulence of the heliosheath, or detected the density jump at the heliopause. The edge of the heliosphere was a theoretical construct, one of the most widely accepted and well-supported theoretical constructs in space physics. But theoretical nonetheless. Nobody had been there. Nobody had measured it. Nobody had confirmed that the boundary existed in the form the models described. And then Voyager kept flying. The Voyager program was conceived in the late 1960s to exploit a rare planetary alignment that occurs roughly once every 176 years. During this alignment, the four outer giant planets, Jupiter, Saturn, Uranus, and Neptune, are positioned such that a spacecraft can use the gravity of each world to sling itself toward the next, visiting all four in a single extended mission. This trajectory required precise timing and extraordinary navigation, but it was physically achievable. NASA committed to the endeavor, and in the summer and fall of 1977, two identical spacecraft launched from Cape Canaveral, Florida. Voyager 2 launched first on August 20th. Voyager 1 followed 16 days later, on September 5th, on a faster trajectory that allowed it to overtake its twin. The planetary encounters were spectacular and filled with surprises. Voyager 1 reached Jupiter in March of 1979, returning data that revealed a world far more dynamic than anyone had anticipated. The spacecraft discovered active volcanoes erupting on the moon, Io, the first confirmed extraterrestrial volcanism ever observed. Voyager 2 followed months later, gathering complementary measurements. Both spacecraft continued to Saturn. Voyager 1 arrived in November of 1980 and made a close pass of the giant moon Titan, revealing a world hidden beneath a thick nitrogen atmosphere laced with complex organic chemistry. Voyager 2 reached Saturn the following year, and then pressed onward alone to Uranus in 1986, and Neptune in 1989, becoming the first and still the only spacecraft to visit those distant ice giants. But this story is not about the planets. The planetary encounters were the prologue, not the main act. The most important discovery of the Voyager program came decades later, long after the cameras were powered down and the headlines faded, in a region of space so far from the sun that no human technology had ever sampled it. After Voyager 2 completed its encounter with Neptune in August of 1989, the Grand Tour was finished. Both spacecraft had accomplished every objective of their original mission. They had delivered more discoveries about the outer planets than any mission before or since. The cameras were switched off. Several instruments designed specifically for planetary science were deactivated to conserve the slowly declining power supply. The public attention that had followed the planetary encounters faded. The headlines moved on to other things. The two probes were alone in the outer solar system, far from any world worth photographing, still transmitting their thin radio signal back to Earth, still powered by the slow radioactive decay of plutonium-238 in their onboard radioisotope thermoelectric generators, and still moving outward at tremendous speed. Nothing was slowing them down, nothing was pulling them back. Gravity was still tugging, but their velocity far exceeded the sun's escape speed at that distance. They were on permanent escape trajectories, heading outward forever, bound for interstellar space, whether anyone had planned it or not. Voyager 1 deflected northward out of the plane of the planets by its Saturn encounter, was heading outward at approximately 17 kilometers per second relative to the sun. That is roughly 38,000 miles per hour. It sounds fast, and by human standards it is extraordinarily fast. But at that speed, crossing a single astronomical unit, the distance from Earth to the sun takes roughly 3 months, and the edge of the heliosphere was estimated to lie somewhere between 100 and 150 astronomical units away. The journey to the boundary would take decades, even at Voyager's speed. Voyager 2 was heading in a different direction, southward and at a slightly slower pace of approximately 15.4 kilometers per second. It would approach a different section of the heliosphere's boundary than its twin, providing scientists with an invaluable second data point for comparison. NASA made the decision to continue operating both spacecraft under a new designation, the Voyager Interstellar Mission. It was an act of scientific optimism. No one could guarantee the spacecraft would survive long enough to reach the boundary, but the opportunity was too extraordinary to abandon. The instruments that remained active were the magnetometer, which measures the strength and direction of the surrounding magnetic field, the cosmic ray subsystem, which counts high-energy particles arriving from outside the solar system, the low-energy charged particle instrument, which tracks particles at lower energies, and the plasma wave subsystem, which detects oscillations in the plasma environment around the spacecraft. These four instruments were precisely the tools needed to detect an invisible boundary made of particles, plasma, and magnetic fields. The question was no longer whether the boundary existed. The physics was too solid for any serious doubt. The question was where exactly it lay, what crossing it would actually look like in the data, and whether the spacecraft would still be alive and transmitting when they finally reached it. And so Voyager flew on. Through the quiet years of the 1990s, when few outside the mission team paid attention. Through the turn of the millennium, when the spacecraft were already farther from the sun than any functioning probe had ever been. Through the first decade of the 21st century, as the instruments continued their patient, automated measurements, and the data trickled back to Earth, one bit at a time across an ever-widening gulf of space, year after year after year. The sun shrinking behind them to a point of light, the solar wind thinning around them, the instruments patiently recording the slow, steady changes in the environment that surrounded two small machines, each weighing less than a ton, drifting alone through a darkness deeper than any human being has ever experienced. The solar wind was weakening with distance, not vanishing, but losing its grip. The density of solar particles drops with the square of the distance from the sun. At 10 astronomical units, the solar wind is already 100 times thinner than at Earth's orbit. At 50 astronomical units, 2,500 times thinner. At 90 astronomical units, roughly 8,000 times thinner. The sun's breath was fading. The magnetic field embedded in that breath was stretching and loosening, its spiral pattern widening, its grip on the surrounding space becoming tenuous. And as the solar wind weakened, something else was growing stronger. Galactic cosmic rays. These are not rays in the everyday sense. They are subatomic particles, mostly protons and heavier atomic nuclei, that have been accelerated to extraordinary energies by violent events throughout the Milky Way. Supernova explosions, the shock waves those explosions send rippling through the interstellar medium, the intense magnetic fields of neutron stars and other collapse remnants. All of these processes fling particles outward at speeds approaching the speed of light. These galactic cosmic rays pervade interstellar space. They exist everywhere outside the heliosphere, streaming through the galaxy in every direction. But inside the heliosphere, the sun's magnetic field and solar wind act as a partial shield against these galactic intruders. The tangled, outward-flowing magnetic field deflects and scatters many incoming cosmic ray particles, and the supersonic solar wind itself pushes back against them. The result is that the intensity of galactic cosmic rays inside the heliosphere is significantly lower than in interstellar space. The shielding is not complete. The most energetic cosmic rays, particles carrying billions or even trillions of electron volts of energy, punch straight through regardless. But for the lower energy portion of the cosmic ray spectrum, the heliosphere provides meaningful protection. This shielding effect is called solar modulation, and it varies with the sun's activity cycle. During solar maximum, when the magnetic field is strongest and most tangled, fewer cosmic rays get in. During solar minimum, more leak through. The deeper inside the heliosphere you are, the stronger the cumulative shielding. Earth, sitting at 1 astronomical unit from the sun, receives significantly fewer cosmic rays than a location at 50 or 100 astronomical units, where the shield has thinned considerably. As Voyager moved outward through the outer heliosphere, this shielding effect was steadily diminishing. The instruments tracking galactic cosmic rays recorded a gradual but unmistakable increase, year after year, decade after decade. The count was climbing. The shield was getting thinner. The edge was getting closer. But nobody could say exactly how much closer. The position of the termination shock and the heliopause depends on the balance between the solar wind's outward pressure and the interstellar medium's inward pressure, and both of these quantities are difficult to pin down precisely. The solar wind varies with the sun's 11-year cycle, strengthening at solar maximum and weakening at solar minimum. The interstellar medium's pressure depends on its local density and magnetic field strength, which were known only through indirect estimates. Theoretical predictions for the distance to the termination shock ranged from about 75 to over 100 astronomical units. The heliopause could be anywhere from 100 to 150 astronomical units out. These are enormous uncertainties when you are crossing 1 astronomical unit every few months, and the data is changing slowly. So Voyager moved outward through the darkness, watching the numbers on its instruments creep in directions that pointed toward a boundary it could neither see nor precisely locate. The solar wind thinning, the cosmic rays climbing, the magnetic field evolving. Every data point was a clue. But the edge itself remained invisible, its distance uncertain, its exact nature still a matter of theoretical prediction rather than direct observation. And then, in the early 2000s, the numbers began changing faster. The cosmic ray count on Voyager 1 started climbing more steeply, around 2002 and 2003, at a distance of roughly 85 to 90 astronomical units from the Sun. Energetic particles from multiple sources showed simultaneous increases that persisted for months. Galactic cosmic rays, anomalous cosmic rays, and lower energy ions all surged together. Something was different now. The spacecraft was approaching a region where the solar wind was losing its long battle with the interstellar medium. The balance was shifting. The instruments were picking up the first signals of a boundary that no human technology had ever directly touched. The termination shock was near. The first layer of the edge was just ahead, somewhere in the darkness, invisible to every instrument except the ones that could feel the particles and fields shifting around the spacecraft. Scientists on Earth were watching the data arrive, one transmission at a time, each round-trip signal taking more than 24 hours to complete at that distance. They knew the crossing was coming. They did not know exactly when. They did not know exactly what it would look like. And they did not yet realize that what Voyager would measure when it crossed that threshold would surprise nearly everyone who had spent decades predicting what the edge should look like. On December 16th, 2004, at a heliocentric distance of approximately 94 astronomical units, something happened to the data streaming back from Voyager 1. The numbers did not change gently. They did not drift or waver the way they had been doing for years. They lurched. The magnetic field strength jumped. The intensity of low-energy particles surged. The character of the solar wind, which had been a fast, steady, supersonic outflow for the spacecraft's entire 27-year journey outward, suddenly and dramatically transformed. The solar wind did not stop. It slowed. It compressed. It heated. The flow went from supersonic to subsonic in a transition so abrupt that Voyager 1 passed through it in a matter of hours. After more than a quarter century of flying through a uniform stream of solar particles, the spacecraft had hit something. Not a solid wall, not a barrier you could see, but a shock wave standing permanently in space, separating the fast inner solar wind from the slow, compressed, turbulent outer region beyond it. The boundary was invisible, but its effects on the instruments were unmistakable. Voyager 1 had crossed the termination shock. It was the first human-made object to reach the place where the sun's supersonic breath finally falters. To appreciate what happened, you need to understand what the termination shock actually does to the solar wind. Inside the shock, the solar wind is moving at roughly 400 kilometers per second. It reached that speed in the sun's corona, and nothing in the thin space between the planets has offered enough resistance to slow it down. The solar wind in the inner and middle solar system is fast, hot, and freely expanding, like a river rushing downhill without obstruction. But as it pushes farther and farther from the sun, it is running into the mounting back pressure of the interstellar medium, the galactic gas and magnetic field pressing inward from all sides. Eventually, at some critical distance, the solar wind can no longer push through that resistance at supersonic speed. It hits a shock front, a permanent standing wave in space, and decelerates sharply. On the far side of the shock, the solar wind has slowed to roughly 100 kilometers per second or less. Its temperature has jumped enormously. Its density has increased as the plasma compresses. The once free-flowing wind becomes a sluggish, turbulent, heated mass that is no longer streaming outward cleanly, but is instead piling up against the boundary ahead. Voyager 1 felt all of this. The cosmic ray subsystem recorded a sharp spike in the intensity of lower energy particles, ions that have been accelerated by the shock itself. The magnetic field instrument showed a sudden increase in field strength as the plasma compressed on the far side of the transition. The low energy charged particle detector registered dramatic changes in the particle populations around the spacecraft. Everything pointed to the same conclusion. The spacecraft had punched through the termination shock and entered the heliosheath, the outermost layer of the heliosphere, the turbulent region between the shock and the outer boundary beyond. But in the midst of all that confirmation, there was a surprise. And it was a significant one. For decades, one of the central predictions about the termination shock involved a type of particle called anomalous cosmic rays. These are not ordinary galactic cosmic rays. They are particles that originate as neutral atoms in the interstellar medium, drift into the heliosphere because they carry no charge and are unaffected by the sun's magnetic field, then become ionized by a solar ultraviolet radiation or charge exchange. Once ionized, They are picked up by the solar wind and carried outward. Theory held that when these newly ionized particles reach the termination shock, they would be accelerated to high energies by bouncing back and forth across the shock front. A well-understood process called diffusive shock acceleration. The termination shock was supposed to be the primary factory for anomalous cosmic rays. Their intensity was expected to peak right at the shock, reaching a maximum at the exact location where Voyager crossed through. That is not what happened. When Voyager 1 crossed the termination shock, the intensity of anomalous cosmic rays did not peak. It did not reach a maximum. In fact, the energy spectrum of these particles looked nothing like what diffusive shock acceleration at that location should have produced. The anomalous cosmic rays were there, but they were not being accelerated at the shock in the way that decades of theoretical work had predicted. Their source, wherever it was, appeared to be elsewhere, perhaps at a different part of the termination shock, far from Voyager 1's crossing point, perhaps through a mechanism that did not match the standard model. This was deeply puzzling. The termination shock was supposed to be the answer to the anomalous cosmic ray question. Instead, it deepened the mystery. Theorists scrambled to explain the discrepancy. Some proposed that the acceleration was happening at different locations along the shock surface, where conditions were more favorable. Others suggested that the shock itself was weaker than expected, which would reduce its ability to accelerate particles efficiently. And there was growing evidence that pickup ions, interstellar atoms that drift into the heliosphere as neutral particles, become ionized by solar ultraviolet light, and are then swept outward by the solar wind, were playing a much larger role in the physics of the termination shock than anyone had anticipated. These pickup ions carry enormous amounts of thermal energy. Research using data from the New Horizons spacecraft, which carried a dedicated pickup ion detector called the Solar Wind Around Pluto instrument, later showed that by approximately 20 astronomical units from the Sun, pickup ions were already providing the dominant internal pressure in the solar wind, far exceeding the thermal pressure of the solar wind protons themselves. They were mediating the shock, absorbing its energy, weakening it, changing its character in ways that the earlier models had not fully accounted for. The termination shock was softer and more complex than the clean, strong discontinuity that textbook physics had led scientists to expect. The termination shock was real. Voyager had confirmed its existence beyond any reasonable doubt. But it was not the clean, strong, well-behaved structure that theory had predicted for half a century. It was messier, weaker, and stranger than expected. The edge of the solar system was already defying the textbooks at its very first layer, and Voyager had only crossed one of the three boundaries that separated the Sun's domain from the galaxy beyond. 3 years later, in August of 2007, Voyager 2 reached the termination shock at a different point in space. Its crossing occurred at a heliocentric distance of approximately 84 astronomical units, roughly 10 astronomical units closer to the Sun than Voyager 1's crossing. That 10 astronomical unit difference was immediately significant. It meant the termination shock was not a fixed, rigid boundary sitting at a single distance from the Sun. It was a moving structure, pushed outward when the solar wind was strong and squeezed inward when the solar wind was weak. The Sun's output varies over its roughly 11-year activity cycle, and that variation was enough to shift the position of the termination shock by billions of miles. But Voyager 2 brought something to the crossing that its twin did not have: a working plasma science instrument. And the data it returned from the termination shock was invaluable. Voyager 2's plasma instrument directly measured the solar wind speed dropping from supersonic to subsonic as the spacecraft crossed the shock. It recorded the corresponding increase in plasma density and temperature on the downstream side. It measured the detailed structure of the transition, revealing that the shock was not a single clean discontinuity, but a complex, layered structure with multiple crossings, as though the shock surface was rippling back and forth across the spacecraft's path. The termination shock at Voyager 2's crossing point appeared to be a dynamic, unsteady boundary that was not sitting still. This was consistent with the evidence from Voyager 1's crossing, where the spacecraft had appeared to cross the shock multiple times in quick succession. The termination shock was not a frozen feature of space. It was a living, breathing, fluctuating boundary that shifted in response to changes in the solar wind and the interstellar medium. This is worth pausing on because the presence or absence of this single instrument, the plasma science experiment, would shape the entire drama of everything that followed in Voyager 1's journey. Every spacecraft carries a limited set of instruments, each designed to measure a specific aspect of the surrounding environment. Voyager 1 and Voyager 2 were built as identical twins, carrying the same suite of 10 scientific instruments. But hardware does not last forever, and in 1980, shortly after Voyager 1's encounter with Saturn, its plasma science instrument failed. The device, which directly measured the speed, density, temperature, and direction of the plasma flowing past the spacecraft, stopped returning reliable data. It could not be repaired. There was no service mission. No technician could be sent to swap a circuit board on a spacecraft already billions of miles from Earth. The instrument was dead, and it would remain dead for the rest of the mission. At the time, this seemed like a manageable loss. The plasma science instrument was most valuable during planetary encounters, and Voyager 1 had already completed its planetary mission. But decades later, when the spacecraft reached the outermost boundary of the heliosphere, the consequences of that failure became enormous. The plasma science instrument was exactly the tool needed to make the most direct and unambiguous measurement of the Heliopause crossing, the point where the surrounding plasma shift from solar to interstellar. Without it, Voyager 1 would have to rely on indirect evidence. Particle counts, magnetic field measurements, and plasma wave detections. These could tell you a great deal, but they could not deliver the clean, simple confirmation that a working plasma detector would have provided. Voyager 2, on the other hand, still had its plasma science instrument in full working order. When it crossed the termination shock in 2007, the instrument recorded precise measurements of the solar wind on both sides of the shock. It measured the deceleration directly, capturing the drop in speed from supersonic to subsonic. It measured the increase in density and temperature. It provided the kind of clean, quantitative data that scientists could plug directly into their models. Voyager 2's termination shock crossing was, in some ways, scientifically richer than Voyager 1's, precisely because of that single functioning instrument. But Voyager 2 was traveling more slowly and in a different direction. It would take more than a decade longer to reach the Heliopause. In the meantime, Voyager 1 was already deep in the heliosheath, pushing toward the outer boundary, carrying instruments that could measure particles and fields, but could not directly sample the plasma. The heliosheath turned out to be a far stranger place than anyone had expected. Beyond the termination shock, the solar wind does not simply slow down and continue outward in an orderly fashion. It becomes chaotic. The plasma, now subsonic and compressed, piles up against the increasing resistance of the interstellar medium ahead, and it has nowhere to go but sideways. The flow that was once radially outward starts turning, deflecting toward the flanks and tail of the heliosphere, pushed aside by the interstellar pressure that grows stronger with every astronomical unit. The magnetic field, which was already complex from the sun's rotation and the spiral pattern it creates, becomes even more disordered on the far side of the shock. Field lines twist, fold, and reconnect. The plasma temperature fluctuates wildly, sometimes spiking to hundreds of thousands of degrees and then dropping again. The density varies from month to month in ways that were difficult to predict or explain from Earth. If the inner heliosphere is like a steady wind blowing outward from the sun, the heliosheath is like the turbulent zone, where that wind meets an immovable wall of air and breaks apart into eddies and currents, swirling in every direction. It is a transitional region in the truest sense, not calm, not stable. A place where two vast and incompatible environments, the solar and the galactic, collide in slow motion across billions of miles. Voyager 1 spent nearly 8 years crossing the heliosheath. Think about that timescale. 8 years of traveling at 17 kilometers per second, covering roughly 3.5 astronomical units per year, through a region that no instrument had ever sampled. 8 years of data streaming back to Earth at the speed of light, each one-way transmission taking progressively longer as the spacecraft receded. The round-trip communication delay stretching past 30 hours by the time Voyager reached the far side of the heliosheath. And during those 8 years, the models that had been built to predict what the heliosheath should look like offered less and less useful guidance with every passing year, because those models had been built on assumptions that the termination shock crossing had already begun to undermine. The real heliosheath was not matching the theoretical heliosheath. It was more turbulent, more variable, more dynamic, and more difficult to interpret than the equations had suggested. The data arriving at Earth from Voyager 1 during those years painted a picture of an environment in constant flux. Magnetic field measurements showed sectors and reversals and compressions that did not match the smooth, orderly transition the simpler models had predicted. The low-energy charged particle instrument recorded populations of ions and electrons that shifted in intensity and composition over time, sometimes in response to events traceable back to solar activity that had occurred months or years earlier. A coronal mass ejection launched from the Sun would take more than a year to reach Voyager's location, but when it arrived, it would compress the local plasma, alter the particle populations, and send a pulse of disturbance rippling through the heliosheath. The heliosheath was alive, not biologically of course, but dynamically. It was a region where the dying breath of the solar wind, weakened by billions of miles of expansion, met the implacable pressure of the interstellar medium and produced a chaotic, variable, turbulent transition that defied simple description. And through it all, the galactic cosmic ray count kept climbing. This was the single most telling signal in the entire dataset. Galactic cosmic rays, the high-energy particles that originate outside the heliosphere from supernovae and other violent astrophysical events across the galaxy, are partially blocked by the heliosphere's magnetic field and solar wind. Inside the heliosphere, their intensity is reduced by the shielding effect of the sun's bubble. Outside it, they reach their full, unmodulated interstellar values, the raw background radiation of the Milky Way. The closer Voyager got to the outer boundary, the less shielding remained between the spacecraft and the unfiltered cosmic ray environment of the galaxy. The cosmic ray count was, in essence, a proxy for how close Voyager was to the Heliopause. And year after year, through 2005, 2006, 2007, 2008, 2009, the count kept going up. Not dramatically in any single month, not in sudden jumps, but the trend was unmistakable, a slow, persistent rise that said the same thing over and over. The boundary is getting closer. At the same time, the intensity of particles clearly associated with the sun was declining. Energetic ions that had been accelerated at the termination shock, particles born from solar wind interactions, the remnants of the sun's direct influence on the local particle environment, all of these were fading. Not vanishing overnight, but diminishing gradually, as if the sun's grip on the surrounding space was loosening, finger by finger, with each additional astronomical unit Voyager crossed. The two trends were mirror images of each other, one rising steadily, one falling steadily, and somewhere ahead, at a distance no one could precisely predict, they would converge at the Heliopause, the place where the last trace of solar particle dominance finally gives way to the full, unshielded galactic background. But the convergence was slow, and predicting exactly when it would arrive was frustratingly impossible. The rate of change fluctuated with the sun's activity and with the complex, unpredictable dynamics of the heliosheath itself. Sometimes, the cosmic ray count would plateau for months, suggesting the boundary was still far away. Other times it would surge unexpectedly, suggesting something was imminent. And then it would plateau again. The heliosheath was not cooperating with anyone's timeline or anyone's model. Then, beginning in 2010, the instruments on Voyager 1 started showing something genuinely new. The spacecraft, now more than 113 astronomical units from the Sun, entered a region where the radial component of the solar wind speed appeared to drop to zero. The plasma, as inferred indirectly through the anisotropy of energetic particle flows, was no longer moving outward. It was moving sideways, deflecting along the boundary or not moving at all. This was unexpected. Even in the heliosheath, models predicted that the plasma should retain some outward component of its flow, gradually slowing but never quite reaching zero until the heliopause itself. But the data was suggesting that the outward flow had already ceased, as though the plasma at Voyager 1's location had reached a stagnation point, a dead zone where the outward push of the solar wind had been completely neutralized by the inward pressure of the interstellar medium pressing against the heliosphere from outside. At the same time, the magnetic field intensity was increasing. The field lines were being compressed, squeezed tighter together as the plasma piled up against whatever lay ahead. It was as though the heliosheath was becoming a narrowing corridor, the plasma crowding into a smaller and smaller volume as the boundary approached. Scientists began debating intensely. Was Voyager 1 approaching the heliopause? Was it about to cross? Could it have already crossed without the team realizing it? Some researchers argued that the stagnation of the radial flow was a strong sign that the boundary was imminent, perhaps only a few astronomical units ahead. Others cautioned that the heliosheath was more complex than anyone had anticipated, and that unusual flow patterns did not necessarily mean the heliopause was near. Without a working plasma science instrument on Voyager 1, determining the actual density of the surrounding plasma, the single most diagnostic measurement for confirming a heliopause crossing, was agonizingly difficult. In 2012, the situation escalated dramatically. In May and then again in late July and August, the galactic cosmic ray intensity on Voyager 1 began surging sharply, rising faster than at any point in the mission's history. At the same time, the count of heliospheric energetic particles born from solar interactions and accelerated at the termination shock, plummeted toward zero. These two changes happened in near lockstep, rising and falling together in a pattern that had never been observed before. The transitions were abrupt, occurring over days rather than the weeks or months that had characterized earlier changes in the heliosheath. It looked as though the spacecraft was punching through a boundary, entering a region dominated entirely by galactic particles rather than solar ones, and then falling back multiple times as the boundary itself rippled and shifted, position around the spacecraft's trajectory. The heliopause, it seemed, was not sitting still. It was moving, oscillating, pushed and pulled by fluctuations in the pressure balance between the solar wind and the interstellar medium. Between July and September of 2012, the data from the cosmic ray subsystem and the low-energy charged particle instrument was painting a picture that was difficult to interpret as anything other than a boundary crossing. The galactic cosmic ray intensity spiked to levels consistent with what scientists expected in interstellar space. The solar particle count dropped to background levels. By every particle measurement available, Voyager 1 appeared to have left the heliosphere. But there was a problem. The magnetic field had not changed direction. For decades, models had predicted that crossing the heliopause should produce a clear, measurable rotation in the direction of the surrounding magnetic field. Inside the heliosphere, the magnetic field is wound into the Parker spiral by the sun's rotation, oriented roughly in the plane of the solar equator. Outside the heliosphere, the magnetic field belongs to the interstellar medium and should be oriented in a completely different direction, determined by galactic scale processes that have nothing to do with the sun. The rotation from one field direction to the other was supposed to be one of the signature confirmations of a heliopause crossing. No rotation was observed. The magnetic field strength changed, increasing noticeably after the particle transitions, but its direction remained essentially the same as it had been inside the heliosphere. The Parker spiral orientation persisted, even as the particles were telling a story of complete environmental change. This contradiction threw the science team into a prolonged and sometimes heated debate that played out in journals, conference halls, and private emails for months. The stakes were enormous. This was potentially the most significant milestone in space exploration since the Apollo moon landings, the first human-made object to leave the sun's bubble and enter interstellar space. Getting the announcement wrong, declaring a crossing that had not happened, or missing one that had, would be a scientific embarrassment of the highest order. Some researchers argued that the particle data was definitive and that Voyager 1 had crossed the heliopause regardless of what the magnetic field was doing. The particles do not lie. If galactic cosmic rays are at interstellar levels and solar particles are at zero, you are in interstellar space. The magnetic field direction must have some other explanation. Others countered that the absence of a magnetic field rotation was deeply troubling, and suggested that perhaps Voyager 1 had entered some new, unexpected region that was neither fully inside the heliosphere nor fully outside it. A kind of transitional zone or boundary layer that nobody's model had predicted. A few researchers proposed that Voyager 1 might have entered a magnetic highway, a channel where the sun's field lines connected to interstellar field lines, allowing particles to flow freely between the two environments while the field direction remained unchanged. The debate consumed the better part of a year. Scientific papers were published arguing both sides. Press conferences were held and then carefully qualified. The public was confused. The scientists were, if they were honest with themselves, also confused. And the root cause of the confusion, the reason the question could not be settled quickly and cleanly, was always the same: that single broken instrument. If Voyager 1 had been able to measure the plasma density directly, a sudden jump from heliospheric values to interstellar values would have ended the argument immediately, but it could not make that measurement. The tool that would have provided the cleanest, most unambiguous answer was the one that had failed in 1980, 3 decades before the spacecraft reached the place where that measurement mattered most. The resolution would come, but it would come from an unexpected direction. Not from the cosmic ray instrument, not from the magnetic field sensor, not from the low-energy particle detector. The answer was hiding in the data from the plasma wave subsystem, an instrument designed to listen to electrical oscillations in the surrounding plasma. It was not the tool anyone had expected to settle the biggest question in heliophysics. But in the absence of a working plasma detector, the plasma wave instrument turned out to be the only device on Voyager 1 capable of measuring the electron density of the surrounding medium, and electron density was the one measurement that could definitively distinguish heliospheric plasma from interstellar plasma. All the instrument needed was something to make the surrounding plasma ring, some disturbance strong enough to set the local electrons oscillating at their natural frequency. And more than a year earlier, without anyone realizing its significance at the time, the Sun had obliged. A massive coronal mass ejection, a billion-ton eruption of solar plasma and magnetic field, had been hurled outward from the Sun in March of 2012. It had been racing outward from the Sun, decelerating as it pushed through the increasingly dense heliosheath, and it was headed directly for Voyager 1's location. It would take more than a year to cross that enormous distance. When it did, it would either confirm or deny that Voyager 1 had crossed the Heliopause. And what the plasma wave instrument heard when that eruption finally reached the spacecraft would settle a debate that had consumed the heliophysics community for months, reveal the density of the medium Voyager 1 was now traveling through, and confirm something that no human being had ever directly verified before: that a human-made object had crossed out of the Sun's domain and into the space between the stars. The eruption was on its way. The instrument was listening, and the answer, when it came, would change everything. In April of 2013, 13 months after it erupted from the Sun, the coronal mass ejection arrived. The billion-ton wave of solar plasma and compressed magnetic field, hurled outward in March of 2012, had been racing through the heliosheath for over a year, crossing billions of miles at hundreds of kilometers per second. And now it reached the location of Voyager 1. The wave slammed into the surrounding medium and compressed it, squeezing the thin plasma around the spacecraft and sending a shudder through the charged particles in Voyager's immediate environment. That compression did exactly what the science team had hoped it might. It set the local electrons vibrating, oscillating at their natural plasma frequency, the frequency at which free electrons in an ionized gas collectively ring when disturbed. The plasma wave subsystem heard it. The instrument detected electron plasma oscillations at a frequency of approximately 2.6 kilohertz. This was not random noise. It was not an instrument artifact. It was a clean, identifiable signal with a very specific physical meaning. In plasma physics, the frequency of electron oscillations is directly related to the density of electrons in the surrounding medium. Higher density means higher frequency. Lower density means lower frequency. The relationship is precise and well understood. A frequency of 2.6 kilohertz corresponds to an electron density of approximately 0.08 particles per cubic centimeter. That number was the key to everything. Inside the heliosphere, at the enormous distances Voyager 1 had been traveling, the typical electron density of the solar wind plasma was roughly 0.002 particles per cubic centimeter. 0.002 of a particle in every cubic centimeter of space. An almost inconceivable sparseness. But the density the plasma wave instrument had just measured was approximately 40 times higher. 0.08 versus 0.002. The gap between those two numbers was the gap between being inside the sun's bubble and being outside it. There was no environment inside the heliosphere at any distance from the sun that could produce an electron density of 0.08 particles per cubic centimeter. It simply did not exist in the solar wind at 122 astronomical units. But an electron density in that range was entirely consistent with the expected density of the very local interstellar medium, the thin galactic plasma that fills the space between the stars in our neighborhood of the Milky Way. Decades of indirect observations and theoretical modeling had predicted interstellar densities in roughly this range, and now a spacecraft was measuring it directly, in place, for the first time. The lead scientist on the plasma wave instrument, Donald Gurnett at the University of Iowa, later described the moment his team saw the data. They jumped out of their seats. The oscillations were unmistakable. The frequency was clean. The density it implied was interstellar. There was no other interpretation that fit. The science team went back through earlier data from the plasma wave instrument and found something they had initially missed. A fainter, shorter set of electron oscillations had been recorded months earlier, in October and November of 2012. Those earlier oscillations corresponded to a slightly lower density, suggesting the spacecraft had been in a transitional region at that time. But the density was still far higher than anything inside the heliosphere could produce. By tracing the density measurements backward in time and combining them with the particle data from the cosmic ray subsystem and the low-energy charged particle instrument, the team was able to reconstruct the timeline. Voyager 1 had crossed the Heliopause on or around August 25th, 2012, at a heliocentric distance of approximately 122 astronomical units, roughly 11 billion miles from the Sun. On September 12th, 2013, more than a year after the crossing itself, NASA held a press conference and made the announcement that the heliophysics community had been building toward for decades. Voyager 1 had entered interstellar space. It was the first human-made object to leave the sun's protective bubble and directly sample the environment between the stars. The announcement came with a specific date, August 25th, 2012. A specific distance, approximately 122 astronomical units, and a specific measurement, the plasma electron density, that served as the definitive confirmation no other instrument could have provided. The decades of theoretical prediction, the years of painstaking data analysis, the months of contentious scientific debate, all of it converged on a single conclusion supported by every available line of evidence. Voyager 1 was no longer inside the sun's domain. It was outside, measuring the galaxy's plasma and fields and cosmic rays for the first time in the history of human exploration. The announcement reverberated around the world. It was, in the plainest terms, a milestone unlike any other in the history of spaceflight. Humans had sent probes to other planets, landed robots on Mars, dropped instruments into the atmospheres of Jupiter and Titan. But no machine had ever left the sun's bubble. No instrument had ever directly touched the interstellar medium. Voyager 1 had done both, with technology designed in the early 1970s, running on a power source that was slowly dying, communicating with Earth through a radio signal so faint that the energy it delivered to the receiving antenna was measured in billionths of a watt. But confirmation did not mean simplicity. The crossing raised at least as many questions as it answered, and the first and most persistent of those questions was the magnetic field. But there was still the lingering puzzle. The direction of the magnetic field surrounding Voyager 1 had not rotated when the spacecraft crossed the Heliopause. The particle data was unambiguous. Solar particles vanished, galactic cosmic rays surged, electron density jumped by a factor of 40. By every particle-based measure, Voyager 1 was in a completely different environment. But the magnetic field, the invisible web of force that permeates space and is carried by the plasma, continued pointing in essentially the same direction it had been pointing inside the heliosphere. The Parker spiral orientation, the characteristic signature of the sun's magnetic field, wound outward by solar rotation, persisted. This was not supposed to happen. The interstellar medium has its own magnetic field, oriented in a direction determined by galactic scale processes, completely unrelated to the sun. Models had predicted that crossing the heliopause would produce a clear, measurable rotation from the solar field direction to the interstellar field direction. That rotation would have been the cleanest possible signature of the crossing, a compass needle swinging from one heading to another as you step across the boundary. But the compass did not swing. The field direction held steady, even as every other measurement confirmed the crossing. For years, this anomaly resisted a satisfying explanation. Several hypotheses were proposed. Perhaps the interstellar magnetic field near the heliopause happened to be oriented in nearly the same direction as the heliospheric field at Voyager 1's location. An unlikely but not impossible coincidence. Perhaps the field was being draped around the heliosphere by the interaction between the sun's bubble and the interstellar flow, aligning itself parallel to the boundary surface in a way that mimicked the interior field direction. Perhaps the spacecraft was in a transitional region where the two fields had partially merged through magnetic reconnection, a process in which magnetic field lines from different sources break apart and reconnect in new configurations, releasing energy and mixing the field topology. None of these explanations was fully satisfying, and the puzzle only deepened when Voyager 2 crossed the heliopause 6 years later and observed the same thing. On November 5th, 2018, Voyager 2 reached the heliopause at a heliocentric distance of approximately 119 astronomical units, roughly 3 astronomical units closer to the Sun than Voyager 1's crossing point. The two spacecraft had crossed the boundary at locations separated by more than 100 astronomical units of lateral distance and traveling in different directions. Voyager 1 heading northward and Voyager 2 heading southward. The crossings sampled two widely separated regions of the Heliopause, and both occurred on the nose side of the heliosphere, the leading edge of the Sun's bubble as it plows through the interstellar medium. And this time, the crossing came with something Voyager 1 could not provide. Clean, direct, definitive plasma measurements from a fully functioning plasma science instrument. The data from Voyager 2's crossing was transformative. The plasma science instrument recorded a steep decline in the speed of the solar wind on November 5th. Within a single day, the radial speed of the outflowing solar plasma dropped effectively to zero. The solar wind, which had been streaming outward from the Sun for billions of miles, slowing and weakening but never quite stopping, finally stopped. On the far side of the transition, the instrument measured not solar wind plasma, but interstellar plasma. Denser, cooler in some ways, but also unexpectedly hot, and flowing in a direction consistent with the motion of the local interstellar medium past the heliosphere. The density jump was striking. Inside the heliosphere, near the heliopause, the plasma density measured by Voyager 2 was roughly 0.002 particles per cubic centimeter. The same sparse, exhausted solar wind that had been thinning for billions of miles. Outside the heliopause, the density jumped to approximately 0.04 particles per cubic centimeter, as directly measured by the plasma science instrument. The plasma wave instrument on Voyager 2 later measured an electron density of approximately 0.039 particles per cubic centimeter at a slightly greater distance, confirming the plasma instrument's reading with an independent method. The jump was roughly 20-fold. From one side of the boundary to the other, the density of charged particles increased by a factor of 20 in less than a single day of travel. The heliospheric plasma and the interstellar plasma are two genuinely different environments, separated by a boundary that is remarkably thin in some of its properties. But the crossing was not entirely abrupt. Voyager 2's plasma instrument revealed structure within the transition. A boundary layer approximately 1.5 astronomical units wide was detected before the heliopause proper. In this pre-boundary region, the heliosheath plasma slowed, heated up, and became roughly twice as dense as typical heliosheath conditions. The plasma was piling up against the approaching wall of interstellar gas, compressing and warming before the final transition. Then the heliopause itself was crossed, with the solar wind speed dropping to zero and the interstellar plasma appearing on the instrument in a clean, decisive step. The layered structure, a broad pile-up region followed by a sharp final transition, was something the models had not predicted with this level of detail. Voyager 2 was showing that the heliopause is not a single, simple surface. It has internal structure, with a gradual approach zone leading to a relatively sudden final boundary. But it was the temperature measurement that caught everyone off guard. Models of the very local interstellar medium had predicted a temperature of roughly 15,000 to 30,000 Kelvin, based on decades of indirect measurements and theoretical calculations. These models drew on observations of interstellar absorption lines in the spectra of nearby stars, which provided estimates of the temperature and velocity of the interstellar gas flowing through our galactic neighborhood. The models were well established and had been refined by multiple independent research groups over years. The temperature of the local interstellar cloud was considered one of the better constrained parameters in heliospheric science. Voyager 2 measured a temperature between 30,000 and 50,000 Kelvin. The interstellar medium just outside the Heliopause was significantly hotter than predicted. At its highest readings, the measured temperature was nearly twice the upper end of the model range. This was not a marginal discrepancy. It was a clear indication that something was happening at the boundary that the models had not accounted for. The most likely explanation is compression heating. The heliosphere does not sit passively in the interstellar medium. It pushes into it. The Sun is moving through the local interstellar cloud at approximately 26 kilometers per second, and the heliosphere, inflated by the solar wind, acts as an obstacle in the interstellar flow. The interstellar plasma that encounters the heliosphere's outer surface is compressed, squeezed, and heated by the interaction, much like the air in front of a fast-moving vehicle is compressed and warmed. The temperature Voyager 2 measured is consistent with this compression effect. The interstellar medium near the Heliopause is not pristine. It has been modified by the heliosphere's presence, heated by the boundary interaction, altered from its undisturbed galactic state. This is a subtle but important finding. It means that even outside the Heliopause, the Sun's influence is not entirely gone. The heliosphere leaves a mark on the interstellar medium around it, heating and disturbing the galactic gas for some distance beyond the boundary. The transition from solar to galactic is not a clean break. It is a gradual fading that extends outward into the interstellar environment. And just like Voyager 1, Voyager 2 observed no significant rotation in the magnetic field direction at the crossing. The Parker spiral orientation persisted on the far side of the Heliopause, even as every other measurement confirmed that the spacecraft had entered a fundamentally different environment. Two spacecraft, crossing at two different locations separated by more than 100 astronomical units, both observed the same anomaly. The magnetic field direction did not change as expected. Whatever was causing this, it was not a local effect specific to one crossing point. It was something about the Heliopause itself. Beyond the shared magnetic anomaly, the two crossings told strikingly different stories in their fine details, and those differences are themselves a discovery. Voyager 1's crossing was gradual and uncertain. The particle transitions occurred over a period of weeks in the summer of 2012, with the spacecraft appearing to cross and then uncross the boundary multiple times as the Heliopause rippled back and forth across its trajectory. The galactic cosmic ray count would surge to interstellar levels, then partially recede, then surge again. The solar particle count would drop to 0, then briefly recover, then drop again. It was as though the Heliopause was a flexible membrane, pushed outward and pulled inward by fluctuations in the solar wind pressure, and Voyager 1 was threading back and forth across it as it moved. The lack of a working plasma instrument delayed definitive confirmation by more than a year, and left room for debate and alternative interpretations that consumed the scientific community. Voyager 2's crossing, by contrast, was sharp and decisive. The transition happened on a single identifiable day. The plasma instrument recorded a clear, sudden step function in the data. Solar wind on one side, interstellar plasma on the other. The pre-crossing boundary layer was detectable and layered, but the final transition itself was unambiguous. There was far less room for debate, far less ambiguity, and far less scientific drama. The instrument designed to detect this exact transition was functioning, and it delivered exactly the measurement needed. These differences are scientifically valuable precisely because they are different. Voyager 1 and Voyager 2 crossed at two separate locations on the heliosphere's surface, separated by enormous distances and traveling in different directions. The fact that the crossings look different tells scientists that the heliopause is not uniform. Its thickness, its structure, and the sharpness of the transition vary from one location to another. It is not a simple surface that looks the same everywhere. It is a complex, three-dimensional boundary shaped by local conditions, by the strength and direction of the interstellar magnetic field at each point, by the pressure and flow of the solar wind from the inside, and by the dynamics of the interstellar medium pressing in from outside. In 2024, a team of researchers led by Drew Turner published a study in the Astrophysical Journal that proposed a new explanation for the persistent magnetic field mystery. The paper re-examined data from both Voyager crossings and compared the observed magnetic field directions to predictions from 4 different heliosphere models combined with 3 different estimates for the interstellar magnetic field orientation. In every combination, the expected magnetic field direction outside the heliopause was inconsistent with what the Voyagers actually observed. The measured field direction after the crossings did not match the draped interstellar field. It did not match the pristine interstellar field. And over the years following their respective crossings, the magnetic field observed by both spacecraft was actually rotating slowly away from both the expected interstellar direction and the heliospheric direction. The team proposed that both Voyagers had transited not a thin, clean heliopause surface, but a thick boundary layer of reconnected magnetic flux along the heliopause. In this layer, magnetic field lines from the heliosphere and the interstellar medium have broken apart through magnetic reconnection and reformed into new hybrid configurations, mixing solar and interstellar magnetic topology in a region that could be extraordinarily thick. The study estimated that at Voyager 1's crossing location, this boundary layer might be more than 18 astronomical units thick, and likely much thicker. That is an enormous distance, roughly the distance from the Sun to Uranus. At Voyager 1's speed of 17 kilometers per second, crossing 18 astronomical units takes roughly 5 to 6 years. The implication is striking and, for many scientists, unsettling. Voyager 1, which crossed the heliopause particle boundary in August of 2012, may not yet have fully transited the magnetic boundary layer as of the mid-2020s, more than a decade after the crossing. The spacecraft could still be inside a mixed transition zone where solar and interstellar magnetic fields are tangled together by ongoing reconnection processes, not yet in the pristine interstellar medium where the magnetic field reflects purely galactic conditions. That would explain why the magnetic field direction never rotated cleanly. Voyager 1 may never have fully left the Sun's magnetic reach. It has been flying through a thick, magnetically mixed boundary layer this entire time, a region that is interstellar by its particle population, but still partially solar by its magnetic identity. Voyager 2, at its crossing location in the southern hemisphere of the heliosphere, may have encountered a thinner boundary layer. The 2024 study presented evidence that Voyager 2 might already have transited the reconnection layer and entered a region of magnetic field and plasma that was never connected to the Sun, the very local interstellar medium proper. This would make Voyager 2, in a sense, farther into true interstellar conditions than Voyager 1, even though Voyager 1 crossed the particle boundary first and is farther from the Sun. This is still an active area of research, and not all scientists agree with the thick boundary layer interpretation. The heliophysics community remains divided. Some models suggest the heliopause should be thinner than the Turner study proposes, and the magnetic field discrepancy might have other explanations involving the complex draping and deformation of the interstellar field as it wraps around the heliosphere's curved outer surface. Other researchers point out that the magnetic reconnection hypothesis, while compelling, has not yet been confirmed by independent measurements beyond the Voyager data itself. But the 2024 study highlighted a critical point that had been underappreciated for years. The heliopause is almost certainly not a single thin surface. It is a region, a transition zone with real physical depth and internal structure. Crossing it is not like stepping through a doorway. It may be more like walking through a dense fog, a gradual transition from one environment to another, where the exact point at which you can say you have crossed depends entirely on which measurement you are looking at. What both Voyager crossings revealed, taken together, is that the outer boundary of the heliosphere is far more complex than the clean, sharp edge that decades of simplified models had depicted. The textbook picture of the heliopause as a smooth, thin membrane separating solar space from galactic space is, at best, an oversimplification. The real heliopause is layered, variable, and structurally rich. The particle boundary is relatively abrupt. When the solar particles vanish and the galactic cosmic rays reach their full interstellar intensity, that transition happens quickly, over days or less. But the magnetic boundary may be gradual, thick, and internally structured, with ongoing reconnection events creating a mixed field layer that extends for tens of astronomical units in some directions. The plasma boundary is sharp but preceded by a distinct pileup region, where the heliosheath plasma compresses against the interstellar wall. And the temperature of the interstellar medium just outside the heliopause is not what models predicted, running hotter and more variable than expected. Altered by the compression of the heliosphere itself pressing into the surrounding gas, the boundary is not passive. It is an active interface where two fundamentally different environments interact, exchange energy, and reshape each other. The heliopause is real. Voyager confirmed that beyond any doubt. Two spacecraft, decades apart, carrying different sets of functioning instruments, crossed the boundary in different parts of the sky, and both recorded unmistakable transitions from a solar-dominated environment to a galactic one. The edge exists, but it is not a wall. It is not a sharp line drawn across space. It is a dynamic, variable, structurally complex transition zone that expands and contracts with the Sun's activity cycle. Shift position with changes in the interstellar medium, and may be far thicker than anyone imagined before the Voyagers actually flew through it and measured what was there. The data from both crossings also revealed something else. Something that is easy to overlook amid the technical details of particle counts and field rotations and density jumps, but that carries the deeper significance of the entire Voyager interstellar mission. Outside the heliopause, the galactic cosmic ray intensity reached its full, unmodulated value for the first time in any human measurement. This is a point that deserves careful emphasis because it connects everything Voyager measured at the boundary to why the boundary matters for life. Inside the heliosphere, galactic cosmic rays are partially blocked, scattered and deflected by the sun's magnetic field and the outward flowing solar wind. The shielding is not perfect. The most energetic cosmic rays, particles carrying billions of electron volts of kinetic energy, punch through regardless. But for the broader population of lower energy cosmic rays, the heliosphere provides real, measurable protection. The intensity of these particles inside the bubble is significantly lower than the intensity outside it. This has been known indirectly for decades through theory and modeling, but Voyager provided the first direct, in-place measurement of the difference. And the difference was substantial. When Voyager 1 crossed the Heliopause and the galactic cosmic ray count stabilized at its full interstellar value, the data showed that the heliosphere had been blocking a meaningful fraction of the incoming galactic cosmic radiation. The same was confirmed by Voyager 2 6 years later. Every planet inside the heliosphere, including Earth, benefits from the shielding. The heliosphere does not merely define the sun's magnetic territory. It acts as a radiation barrier, reducing the bombardment of high-energy particles that would otherwise stream through the planetary system continuously. The shielding varies with the sun's activity cycle, stronger during solar maximum when the magnetic field is most tangled and active, weaker during solar minimum when the field is more ordered and permeable. But even at its weakest, the heliosphere provides a measurable reduction in the cosmic ray flux reaching the inner solar system. Remove the heliosphere, and the cosmic ray intensity at Earth's orbit would increase significantly. That increase would affect atmospheric chemistry, increase radiation exposure for life on the surface, and potentially alter the conditions for biological evolution over geological timescales. The heliosphere is not merely an abstract boundary interesting only to plasma physicists. It is a shield, a protective structure that has stood between Earth and the raw radiation environment of the galaxy for as long as the sun has been burning. But unpacking what that shield means, how it functions on the scale of the entire solar system, what lies beyond it in the wider galactic environment, and what its existence reveals about our true place in the Milky Way, requires stepping back from the technical details of density jumps and magnetic field rotations and particle counts. It requires seeing the full picture, the one that Voyager's instruments painted across decades of measurements, but that only becomes clear when you assemble all the pieces together and ask the simplest possible question. Where exactly do we live? The crossings have been made. The data is in hand. 2 spacecraft are now flying through the space between the stars, still transmitting, still measuring, their instruments slowly shutting down one by one as the plutonium power fades and the engineers on Earth make harder choices with every passing year. What Voyager found at the edge is clear. What it means for everything inside the edge is the question that remains. The answer to the question of where we live turns out to be more layered than most people expect. And the first layer is a clarification that matters more than it might seem. When NASA announced that Voyager 1 had entered interstellar space, headlines around the world said the spacecraft had left the solar system. That phrasing is understandable. It is dramatic and concise, but it is not accurate. Voyager 1 crossed the Heliopause. It left the region dominated by the sun's solar wind and magnetic field. It entered the interstellar medium, the thin plasma and dust and magnetic field that fills the space between the stars. But it did not leave the solar system. The solar system, in the gravitational sense, extends far beyond the heliopause. The sun's gravity does not stop at the edge of the heliosphere. Gravity has no boundary. It weakens with distance, following the inverse square law. But it never truly reaches zero. Objects that are gravitationally bound to the sun, objects that orbit it however slowly and however distantly, exist at distances that make the heliopause look close by comparison. The most distant of these objects are thought to reside in the Oort cloud, a vast, diffuse, roughly spherical shell of icy bodies that may extend from roughly 2,000 astronomical units to as far as 100,000 astronomical units from the Sun. No one has ever directly observed an Oort cloud object at those extreme distances. They are too small, too faint, and too far away for any telescope to detect. We infer the Oort cloud's existence from the orbits of long-period comets, icy bodies that occasionally plunge into the inner solar system on elongated orbits, taking thousands or even millions of years to complete, suggesting a vast reservoir of such objects at enormous distances. If the Oort cloud extends to its predicted outer limit, its edge would be more than 1.5 light years from the Sun, a substantial fraction of the distance to the nearest star. Voyager 1, at its current distance of roughly 170 astronomical units, has barely scratched the inner fringe of this vast gravitational domain. It will take Voyager roughly 500 years to reach the inner boundary of the Oort cloud, and roughly 30,000 years to pass through it entirely. So Voyager has not left the solar system. It has left the heliosphere. And the distinction matters because it reveals that the solar system has more than one edge, and those edges are defined by fundamentally different things. The first edge is the planetary boundary. Neptune, the outermost major planet, orbits at roughly 30 astronomical units. This is the edge that most people picture when they think of the solar system. Beyond Neptune lies the Kuiper Belt, a wide ring of icy bodies extending to roughly 50 astronomical units, where Pluto and its companions orbit. This is the edge of the known planetary and small body architecture. It is the edge of structure, of recognizable orbiting objects that we can photograph and catalogue. The second edge is the heliopause, at roughly 100 to 120 astronomical units, depending on direction and solar activity. This is the edge that Voyager crossed. It is not an edge of objects. It is an edge of influence. The point where the sun's outward flowing wind of charged particles is finally stopped by the inward pressure of the interstellar medium. Inside it, the sun dominates. Beyond it, the galaxy takes over. This boundary has nothing to do with gravity. It has nothing to do with orbiting bodies. It is entirely about the sun's plasma output and the interstellar medium's resistance to it. The third edge, the gravitational edge, is the Oort cloud, extending potentially to 100,000 astronomical units. This is where the sun's gravitational influence finally becomes weaker than the gravitational pull of other nearby stars and the tidal forces of the Milky Way itself. Objects beyond this distance are no longer meaningfully bound to the sun. They drift free. This edge is real in principle, though no Oort cloud object has ever been directly observed at those extreme distances. Its existence is inferred from the orbits of long-period comets, whose trajectories point back to a distant reservoir. These three edges are nested. The planetary edge sits inside the heliospheric edge, which sits inside the gravitational edge. They measure different things and exist at vastly different scales. And the one Voyager crossed, the heliospheric edge, is the one that matters most for understanding what the solar system actually is, because it is the one that defines the boundary of the sun's active protection. The heliosphere is not just a magnetic domain, it is a shield. This was established by Voyager's measurements, and it is worth understanding in its full significance. Galactic cosmic rays are not a minor nuisance. They are high-energy subatomic particles, mostly protons and heavier atomic nuclei, traveling at nearly the speed of light. They are produced by some of the most violent events in the galaxy. Supernova explosions, the jets of matter erupting from black holes, the shock waves that ripple through the interstellar medium when massive stars die. These particles carry enormous kinetic energy. When they strike the atmosphere of a planet, they trigger cascades of secondary particles that rain down to the surface. They can damage DNA. They can ionize molecules in the upper atmosphere, affecting atmospheric chemistry. Over billions of years, they contribute to the mutation rate in biological organisms, influencing the pace and direction of evolution. The heliosphere blocks a meaningful portion of these incoming cosmic rays. Inside the bubble, the sun's tangled magnetic field and outward-flowing solar wind scatter and deflect lower-energy galactic cosmic rays, reducing the flux that reaches Earth's orbit. Earth's own magnetic field provides a second layer of protection, and the atmosphere provides a third. But the heliosphere is the outermost shield, the first line of defense, operating at a scale that dwarfs the other two. Without it, the cosmic ray environment at Earth's distance from the sun would be substantially more intense. The biological implications of that increase are difficult to quantify precisely, but they are not trivial. Higher cosmic ray flux means more ionizing radiation reaching living tissue, more DNA damage, potentially higher rates of cancer and mutation. Every living thing that has ever existed on Earth has existed inside the heliosphere. Every organism from the first single-celled life in the Archean oceans to the most complex animal alive today has developed under the protection of the sun's bubble. The heliosphere is as much a part of Earth's habitable environment as the atmosphere or the magnetic field. It is simply the part that nobody can see, nobody can feel, and until Voyager crossed its boundary, nobody had ever directly measured. And it is not static. The heliosphere breathes with the sun's 11-year activity cycle, expanding when the solar wind is strong and contracting when it weakens. But it also responds to the environment it moves through. The sun is not sitting still in the galaxy. It is traveling through the local interstellar medium at considerable speed, and carrying the heliosphere with it as it goes. The heliosphere plows through the surrounding interstellar gas, and the properties of that gas determine the shape and size of the bubble. If the interstellar medium is denser or carries a stronger magnetic field, the heliosphere is compressed. If the medium is thinner or weaker, the heliosphere expands. This means the heliosphere has not always been the same size or shape. Over the 4.5 billion years since the solar system formed, the sun has completed roughly 20 full orbits around the center of the Milky Way, each one taking approximately 225 million years. Along that path, it has passed through regions of vastly varying interstellar density and magnetic field strength. There have been periods when the sun traveled through relatively empty regions of the galaxy, and the heliosphere may have been larger and more inflated than it is today, providing more shielding and pushing the heliopause farther outward. There have been other periods when the sun plunged through denser clouds of interstellar gas, and the heliosphere may have been compressed significantly. perhaps shrinking enough that the inner planets experienced measurably higher cosmic ray fluxes. Some researchers have proposed links between such heliospheric compression events and extinction episodes or climate shifts in Earth's geological record, though these connections remain speculative and difficult to confirm. What is not speculative is that the Sun is currently passing through a region of the galaxy known as the local interstellar cloud, a warm, partially ionized cloud of hydrogen and helium gas, approximately 30 light years across. This particular cloud is not uniform. It has variations in density, temperature, and magnetic field strength across its volume. The Sun entered this cloud at some point in the past few 100,000 years, and the heliosphere has been shaped by the cloud's properties ever since. The local interstellar cloud is itself embedded within a much larger structure called the local bubble, a cavity in the interstellar medium roughly 1,000 light years across that was carved out by a series of supernova explosions over the past 10 to 20 million years. The interior of the local bubble is extremely tenuous, far less dense than the average interstellar medium in the galactic disk. Because the Sun sits inside this low-density cavity, the heliosphere is currently inflated to a relatively generous size compared to what it would be in a denser region of the galaxy. Research published in recent years has explored the possibility that the solar system may be approaching the edge of the local interstellar cloud, and a notable study by Merav Ofer and Abraham Loeb examined how the solar system's passage near the boundary of the much larger local bubble could alter the heliosphere's properties. If the Sun exits the cloud and enters a region of higher density or stronger magnetic field, the heliosphere's size and structure could change meaningfully. The bubble that protects Earth could shrink. The cosmic ray shielding could weaken. The conditions that life on Earth has enjoyed for hundreds of thousands of years could shift. Not because anything on Earth changed, but because the galactic environment outside the heliosphere changed. This is a slow process by human standards, unfolding over thousands of years. But it is a reminder that the heliosphere is not a fixed feature. It is a response to conditions that are continuously, if gradually, evolving. The shape of the heliosphere itself remains one of the major unsolved questions in heliophysics. For decades, the standard picture was a comet-like shape, a blunt nose on the side facing the Sun's direction of motion through the interstellar medium, and a long tail stretching behind, drawn out by the interstellar flow. This is the shape that the Voyager mission was designed within, and it is the shape that most textbook illustrations still show. But beginning in 2015, computational models developed by Merav Ofer and collaborators at Boston University proposed a fundamentally different geometry. In these models, the Sun's magnetic field plays a much larger role than previously appreciated, confining the heated plasma of the heliosheath into two jets that extend from the Sun's polar regions. The result is a heliosphere shaped less like a comet and more like a croissant, with two distinct lobes rather than a single elongated tail. Other models produce other shapes, including more spherical or potato-like geometries, depending on the assumptions about electron temperature, magnetic reconnection, and neutral atom interactions. The debate is far from settled, and data alone from the two Voyager crossings cannot resolve it. The Voyagers are point measurements, two tiny sampling locations on the vast surface of the heliosphere. They can tell you what the boundary looks like at those two specific spots, but they cannot reveal the global three-dimensional shape of the entire structure. That requires a different kind of observation. This is not merely a question of geometry. The heliosphere's shape determines how galactic cosmic rays are deflected, where the shielding is strongest, and where it thins. A long-tailed heliosphere distributes protection differently from a compact, two-lobed one. Resolving the shape means understanding how effectively the bubble shields the worlds inside it. NASA's Interstellar Mapping and Acceleration Probe, launched on September 24th, 2025, is designed to address exactly this gap in our understanding. Operating from a position at the Lagrange 1 point, approximately 1 million miles from Earth in the direction of the Sun, the probe collects energetic neutral atoms streaming inward from the heliosphere's boundary. These neutral atoms are created when charged particles in the heliosheath undergo charge exchange with interstellar neutral atoms, producing fast-moving particles that carry no electric charge and therefore travel in straight lines, unaffected by magnetic fields along their path. By mapping the arrival directions, energies, and fluxes of these atoms with unprecedented precision, the probe can reconstruct a global image of the heliosphere's boundary from the inside, building a map of the entire structure rather than relying on two isolated point measurements. The probe's imaging capability is roughly 30 times higher in resolution than its predecessor, the Interstellar Boundary Explorer, which has been mapping energetic neutral atoms from Earth orbit since 2008. The mission also studies the solar wind in real time and measures interstellar dust grains that penetrate the heliosphere, providing additional information about the galactic environment beyond the boundary. Early results from the mission may begin to constrain the heliosphere's true three-dimensional shape within the coming years, potentially resolving a question that has been debated with increasing intensity since the Voyager crossings forced scientists to confront how little they truly understood about the bubble they live inside. Meanwhile, the Voyagers themselves are approaching the end of their scientific lives. As of 2026, Voyager 1 carries only two operational science instruments, the magnetometer and the plasma wave subsystem. Every other instrument has been shut down over the past several years to conserve the dwindling electrical power from the spacecraft's radioisotope thermoelectric generators, which lose approximately 4 watts per year as their plutonium fuel slowly decays. The cosmic ray subsystem was turned off in February of 2025. The low-energy charged particle instrument followed in early 2026. Each shutdown buys a little more time for the remaining instruments, but each one also narrows the window through which we can see interstellar space. The engineers at NASA's Jet Propulsion Laboratory are managing the remaining power with extraordinary care and creativity, making increasingly difficult decisions about which heaters to leave on, which subsystems to sacrifice, and how to stretch every remaining watt as far as it can possibly go. They are, in a real sense, performing triage on one of the most important scientific instruments ever built. Voyager 1 is expected to reach 1 light day from Earth on November 18th, 2026. At that distance, a radio signal traveling at the speed of light will take a full 24 hours to cross the gap between the spacecraft and the ground station in Canberra, Australia, the only antenna in NASA's deep space network capable of sending commands to either Voyager. A round-trip communication takes 2 full days. The spacecraft is so far away that by the time Earth receives a status update, Voyager has already moved roughly 1.5 million kilometers farther into interstellar space. The science mission is expected to continue with at least one functioning instrument into the early 2030s, if the hardware holds and the power margins remain sufficient. After that, the electrical output will drop below the threshold needed to operate any scientific instrument or maintain the radio link with Earth. The spacecraft will keep traveling. The outbound trajectory requires no power and no fuel. Voyager 1 will drift silently through interstellar space at 17 kilometers per second, carrying the golden record, carrying the magnetometer boom and the dead instruments and the antenna pointed at a star it can no longer hear and that can no longer hear it, for millions upon millions of years. It will never reach another star system in any time frame that matters for human civilization. The nearest star along its approximate trajectory is still tens of thousands of years of silent coasting away. But the silence of the spacecraft does not diminish what it found while it was still speaking. Voyager's discovery at the edge of the solar system was not a dramatic photograph. There is no image of the Heliopause, no picture of a glowing boundary or a visible wall separating solar space from galactic space. The most important discovery of the Voyager interstellar mission is invisible to every camera ever built. It exists only in the data, in particle counts, plasma densities, magnetic field measurements, and the frequency of electron oscillations detected by an instrument that was never designed to answer the question it ended up answering. What Voyager found is that the solar system has a boundary, not a gravitational boundary, not an orbital boundary, a plasma boundary. A place where the sun's continuous outflow of charged particles, the solar wind that has been blowing since the sun ignited, finally meets the resistance of the interstellar medium and stops. On one side of that boundary, the environment is solar. The particles come from the sun. The magnetic field was born in the sun's interior and carried outward by the solar wind. The cosmic ray flux is reduced by the sun's shielding. On the other side, the environment is galactic. The particles are interstellar. The magnetic field belongs to the Milky Way. The cosmic rays arrive at their full, unmodulated intensity, the raw radiation background of the galaxy. That boundary, the Heliopause, defines the true extent of the sun's active influence on the space around it. And everything inside it, every planet, every moon, every asteroid, every grain of dust orbiting the sun, exists within a protective envelope that the sun itself creates and sustains. The heliosphere is not a passive feature of the solar system. It is an active structure continuously maintained by the sun's energy output, continuously shaped by its interaction with the interstellar medium, continuously breathing with the sun's activity cycle. If the sun's output changed dramatically, the heliosphere would change with it. If the sun died, the heliosphere would collapse. The bubble exists only because the sun keeps inflating it, second by second, year by year, across the billions of years of its life. This is what Voyager revealed. Not that the edge of the solar system is far away, though it is. Not that interstellar space is different from heliospheric space, though it is, but that the solar system, the place we live, is not open space. It is enclosed space. It is a bubble, a cavity carved out of the interstellar medium by the sun's relentless particle wind, held open by continuous energy expenditure, bounded by a real, measurable, physically complex boundary that Voyager detected not with its cameras, but with its particle counters, and its magnetometer, and its plasma wave receiver. And outside that bubble is the galaxy. Not the friendly, distant, decorative galaxy of the night sky. The actual physical environment of the Milky Way's interstellar medium, with its cosmic rays and its interstellar dust, and its magnetic fields, and its cold, dense gas clouds. The environment that has existed for billions of years before the sun formed and will exist for billions of years after the sun dies. The environment from which the solar system was born and into which it will eventually dissolve. Earth has been shielded from the full force of that environment since the heliosphere first formed by a boundary that most people have never heard of, detected for the first time by two small spacecraft that were designed to photograph Jupiter and Saturn, and then were kept running long enough to stumble across the most fundamental boundary in the sun's domain. The heliosphere is not permanent. It is not guaranteed. It is a product of the sun's current state, a middle-aged main-sequence star burning hydrogen in its core, generating the energy that drives the solar wind, sustaining the bubble that protects everything inside it. The sun will not do this forever. In roughly 5 billion years, the sun will exhaust its hydrogen fuel, swell into a red giant, and eventually shed its outer layers and collapse into a white dwarf. Long before that final stage, the solar wind will change. The heliosphere will change with it. And at some point in the distant future, the bubble will weaken, shrink, and eventually cease to exist. On a shorter time scale, the heliosphere is subject to the vagaries of the sun's journey through the galaxy. The interstellar medium is not uniform. It has denser regions and thinner regions, stronger magnetic fields and weaker ones. As the sun moves through these variations, the heliosphere responds. It has likely been compressed and expanded many times over the Earth's history. There may have been periods when the heliosphere was pushed inward so far that the heliopause lay inside the orbits of the outer planets, exposing them directly to the interstellar medium. There may have been other periods when the heliosphere ballooned outward to enormous sizes, providing even more protection than it does today. The heliosphere is a living structure, responsive to conditions that are beyond any human ability to control, embedded in a galactic environment that the sun has been sailing through since before life on Earth began. Voyager did not discover all of this by itself. The theoretical framework for the heliosphere had been developing for decades before the spacecraft reached the boundary. Scientists predicted the termination shock, the heliosheath, and the heliopause long before any instrument confirmed them. What Voyager did was turn those predictions into measurements. It replaced equations with data. It showed that the boundary is real, that it is more complex than the models predicted, that the interstellar medium just outside it is hotter than expected, that the magnetic field does not behave as cleanly as theory suggested, that the transition may involve a thick boundary layer of magnetically reconnected flux that extends for tens of astronomical units in some directions. And in doing so, Voyager answered the question we have been building toward. Where do we live? We live inside a bubble, a real, physical, measurable bubble of solar plasma and magnetic field, carved out of the interstellar medium by the sun's continuous output of charged particles, bounded by the heliopause, shielded from the full intensity of galactic cosmic rays, and moving through the galaxy at 26 kilometers per second. Every human being who has ever lived has lived inside this bubble. Every living thing that has ever existed on Earth has existed under its protection. And until Voyager crossed its boundary and measured what lay on the other side, no human being had ever directly confirmed that it was there. The solar system is not a collection of planets orbiting in empty space. It is a collection of planets orbiting inside a shelter. The shelter is invisible, made of particles and magnetic force rather than glass or steel, but it is as real as any structure ever built. It has walls, or at least a boundary, that Voyager detected and measured. It has an interior where the sun's influence dominates. It has an exterior where the galaxy's environment takes over. And it has a finite lifetime, dependent on the sun's continued ability to sustain it. This is what two small spacecraft, each no larger than a compact car, built in the 1970s for a 4-year planetary tour, discovered by accident over the course of a journey that lasted nearly 50 years and carried them farther from home than any human-made object has ever traveled. They did not photograph the edge, they felt it. They listened to it. They counted the particles on both sides and measured the density of the plasma and tracked the direction of the magnetic field. And what they found is that the solar system has a skin, a membrane, an outer boundary that separates the sun's domain from everything else in the galaxy. And outside that boundary, right now, the full radiation environment of the Milky Way presses inward against the bubble, held back by nothing more than the solar wind blowing outward from a star that has been burning for 4.5 billion years, and will continue burning for roughly 5 billion more. After that, the wind stops, the bubble collapses, and the space that was once shielded becomes once again simply part of the galaxy. But it is not tonight. Tonight the sun is burning, the wind is blowing, the bubble holds, and inside it, on a small rocky world orbiting roughly 1 astronomical unit from the star that sustains the whole structure, life continues under a shield it has never seen, protected by a boundary it cannot feel, enclosed within a bubble that Voyager discovered by flying far enough to find where it ends.